Hello, everyone. My name is Mrs. Ramthan, and we are going to be talking about different types of reactions today. Our objective is that I can identify each type of chemical reaction based on the number of reactants and products. So we're going to look at how many things go into the reaction and how many things come out, types of substances involved. So we're going to be looking at states of matter and what types of compounds they are, and the changes that occur to the matter itself. So there's certain patterns that we can identify that the different elements go through as the reaction occurs. So our first type of reaction is called a synthesis reaction or combination. And the name is really telling us what's happening. We're going to put elements or compounds together to form one product. And those reactants are going to be simpler and the product will be more complex. So whatever is happening, we are putting two things together into one. So in this example that we have here, we have calcium metal, which we can see here. It's kind of a softer metal. It has that lustrous shine. And oxygen gas I'm representing here with these gas tanks, but there is oxygen in the air. So if we burn calcium, potentially in the presence of oxygen, we can create calcium oxide. So notice that the properties of this material, having this white powdery type brittle characteristic, is distinctly different than this pliable, malleable metal that we have over here. So the reaction or combination with oxygen distinctly changes the properties of the substance. So combination is when we put elements or compounds together to form one product that is more complex than the individual components that make it up. So two reactants to one product. So looking at your reactants and products, it's often pretty easy to pick this one out. Now, kind of the opposite of this reaction would be decomposition. To decompose is to break apart. So it is essentially synthesis in reverse. In this case here, we have a compound called copper sulfate pentahydrate. So this is all one substance. This ionic compound has a certain number of water molecules as a part of its structure. Notice the kind of more shiny blue crystals that we see here. When this material is heated, the water breaks apart and breaks off of the ionic compound. And what we see here is a color change to more of a powdery substance that's a lighter whitish green blue, as opposed to this more bright blue that we see here. The water then typically simply escapes as a gas unless something is done to capture it. So we have one reactant breaking apart into two products. And that reactant is going to be more complex, and the products will be less complex because you're breaking them apart. In another example that we have here, I have a compound called potassium chlorate. When we heat it up, we kind of liquefy the substance and we are left behind with liquid potassium chloride, and oxygen gas is driven off as a part of that decomposition. So we started with one reactant that was pretty complex. It had three elements within it. And we finished with two products, a compound with only two elements and then a single element separate. When we look at the forms of matter that are involved with these different reactions, notice that we have a lot of solids, liquids, and gases. So between synthesis and decomposition, lots of those solids, liquids, and gases. That's common for this type of reaction. All right, sorry about that. My daughter's leg was stuck in the crib, so we had to go take care of that. So for these reactants and products, we're really looking at the number of reactants and products and what state of matter they are. Single displacement or replacement, you can see it used both ways, is going to be a replacement or a trading for the pattern. Then my computer decided to run out of space for videos, so had to clear up a little space there. So the trading that's going to occur in single displacement or replacement is between an element and a compound. And there's two different ways it can happen. If the single element is a metal, it is going to trade places with the metal in the compound. Remember that cations come first. So the metal will be in the first position of the compound. That's why in our products here, we see that A is bonded to C and B is kicked out of its spot and is now alone. If A is a nonmetal, it's going to trade places with the nonmetal in the compound. Remember that anions are second in ionic compounds. So we're going to see those two trade places. That's why we see that the single element is in the second position in the final product and C is now by itself. So here we see an example where you could take magnesium metal. I have it kind of pictured here in the ribbon form. And if we would react that with iron 3 chloride, which is kind of a brown clear solution, we would get clear magnesium chloride and we would have kind of flaky floating precipitate of iron metal. So the iron metal would trade places with the magnesium. Magnesium was on its own, and when the iron and the magnesium trade places, the iron is now in its elemental form and the magnesium is now in its ionic form bonded to the chlorine. So notice that we have an element plus an ionic compound to start. And I also finish with that as well. And notice that the ionic compounds are aqueous or dissolved in water. So that's kind of necessary to allow those individual ions that are dissolved in solution to interact with the metal in the reaction. Here we see that we have an example of a nonmetal. If I take chlorine gas and I react it with sodium bromide, the chlorine is going to trade places with the bromine, and I'll get sodium chloride and bromine gas left over. So the like substances switch. So the element that is by itself is the one that's going to determine what trade is going to take place. Notice that we have two reactants and two products in this case. So these are distinctly different from either of the first two reactions that we found. So the first two reactions had either one reactant and two products or two reactants and one product. They weren't the same amounts. Here, it's going to be 2 and 2. Now, what we're going to find is that other reactions also have two reactants and two products. So if you notice that, we're going to have to look more closely at the types of substances involved. Note here, we have a solid with an aqueous solution producing an aqueous solution in a solid. Another type of replacement reaction is called double replacement. So much like single replacement, there's a switch, but this time we have two things switching, and that's where the double is coming from. So here we have two compounds trading partners to produce two more compounds, and there's two classifications of these types of reactions. In one case, we have what's called a neutralization. This is typical for acid-base reactions. And in this case, we have often an acid. Here we see hydrochloric acid in an aqueous solution reacting with a base. Here, this magnesium hydroxide is an ionic compound in aqueous solution. And what we see is that if you want to think of it this way, the positive ions traded places. So even though H is a nonmetal, when it ionizes, it forms a positive ion, which is why it trades places with the magnesium. So we now have magnesium chloride, which remains aqueous, but we formed water, which is a liquid new substance. So when we look for evidence of a chemical change here, we're looking for something to exist differently than it did before. And when substances are aqueous, that's existing differently because they're in their separate ion forms. Whereas when it's in the liquid form, it's a covalently bonded molecule that's like stuck together. So when you form water that's in the liquid state, that's considered a neutralization reaction. Another type of reaction is called precipitation. Now here I have sodium carbonate reacting with calcium chloride. Notice both aqueous solutions. In the pictures here, you can see that they are both clear solutions. When they react and they're placed together, one of the products is NaCl, sodium chloride, but that remains aqueous. So technically, those ions didn't really change. However, calcium carbonate forms a solid. And what we would see is these powdery particles would be visible floating within the clear solution of the aqueous sodium chloride. So the precipitation reaction is the formation of a solid product when you started with two aqueous solutions. So like I said, these kind of powdery particles would become visible floating and kind of chunky in the sodium chloride solution. So we would see that clear solution with the solid particles forming. The properties of this material are such that it is not soluble in water. So when we're looking not soluble, that means it can't be dissolved in water. That's why it forms the solid where there was no solid material in the reactants. So again, we have two reactants to two products. But the difference here is that we have two compounds trading partners, and we get two compounds at the end. Remember up above in single replacement, it was an element and a compound producing a different combination of element and compound. Now our fifth category is one of those that one of these things is not like the other. So combustion is kind of a special case reaction that has a very clear pattern that it follows, but it doesn't qualify as any of the prior four. So with combustion, we specifically have a carbon and hydrogen substance reacting specifically with oxygen gas. So when we look at our word equation, the CXHY means I can kind of have any combination of C's and H's. This is my fuel source. If it is burned in the presence of O2 gas, this little triangle, we saw that before, but I didn't really explain it because that was a point where I was interrupted. This means adding heat or energy. Energy. So when I add energy to this fuel source in the presence of oxygen, I produce CO2 and water every single time. So no matter what combination of C's and H's I start with, I'm going to finish with carbon dioxide and water. I'm also always going to have O2 involved in the reaction. Now, one thing that's kind of typical for combustion reactions is that your coefficients can get really big because we have compounds with many C's and H's that can be involved. So the more C's and H's you have, the bigger that these coefficients may end up getting, because if you end up with an odd number of oxygen on this side, you got to double everything to make the coefficients work out. because if you're working in a unit of O2 on this side, it can get a little bit more challenging to balance. So over here, we have evidence of an alcohol burning. Notice the kind of like bluish flame. Oftentimes the alcohols will burn with a slightly different color flame, but an alcohol would be something like C2H5OH. So if we burn this carbon-hydrogen compound in the presence of oxygen, we get our CO2 in water. Between ethanol and then here, this example, this is glucose. This is actually, if you think back to bio, this is cell respiration. Cell respiration is a very controlled way to do combustion. Combustion is different in that it happens all in one step, and all of that energy gets released as you burn the glucose. So carbon-hydrogen compounds are kind of the basis, but they can also have oxygen within the compound itself. It just changes some of the proportions of the other reactant and products down the line. So you've now learned about 5 different reactions. We started with synthesis. We talked about how things were put together to become more complex. We then mentioned that decomposition is really the opposite of that I'm breaking something complex apart into simpler components. Notice that adding of energy. In a different pattern, we have our displacement reactions that involve trading or switching. I can have a single element trade places within a compound, or I can have 2 compounds trade partners. Both of those have 2 reactants and 2 products. Lastly, we have our combustion. It does still have 2 reactants and products, but there isn't a clear like trading of partners. It can't be classified clearly as a displacement reaction. Notice that these compounds are typically going to be gases and liquids involved, which is another hint that it's not displacement, because displacement reactions typically have aqueous solutions and ionic compounds involved. So at this time, you will wrap up and you will be able to begin practice on classifying as well as additional balancing reactions.